No. Nope. Not gonna make this video though. So you gotta give me a second. Let me make this video, and then we'll go from there.
I just like the sound.
All right, close the door. Hey, what's going on, guys? This is on the Unit 8 for Real World Application for Rational Expressions. It's real world word problems, guys. Don't let it be discouraging to you. Let's go and get started. All right, man. Right here at Real World Application of Rational Expressions. Man, here's your standard, man. We want to create equations and inequalities. All right, in one variable. All right, and use them to solve equations. Okay. So this first one right here. Let's see, is the whole thing in the screen? Now let's make it a little smaller. Boom, there we go. All right. This is our objective, man. I want you to be able to create and solve an equation from a real world application problem. So with this first example, the band members of Archer plan to play at the Sugar Bowl, all right, game in New Orleans this year over winter break. The trip will cost $300 per person, plus per man. Oh my gosh, the trip will cost $350 per band member plus a $2,000 deposit that each member must pay an equal part. All right. So we're going to let's talk about the critical information, man. And I think it's all right here, right? Like they're going to the band members going to play at a football game or winter break. Doesn't really matter. All right, the critical stuff is right here.
I just like the sound.
All right, in this sentence, okay? So, with that being said, it says write a function that represents the total cost of the trip per band member. So let's look at the things we know. We know off the strength, right? We know right now it says the trip will cost $250 per band member. So however many band members it is, if I'm a band member, I have to pay $350. That goes without saying. I am paying $350. All right, because it says per band member. I'm paying $350 if I'm a band member. If you're a band member, you're paying $350. Then it says plus, right? Keyword plus. That tells us we're going to add something, right? Plus a $2,000 deposit that each member must pay an equal part of. Okay? So $2,000 deposit each member must pay a part of, meaning equal part, meaning we got however many band members it is, we need to split this $2,000 up. So we know it's $2,000 and we all got to split it up. All right, so we're going to divide it by however many people there are. If it's 2 of us, we're going to divide that by half. If it's 2,000 of us, we're going to divide that by, you know what I'm saying, $1 a piece. But the point is, we're going to divide this out, okay? And that will be the total that each individual will have to pay. All right, each individual will have to pay. So this is going to be our function, guys. All right, each individual has to pay $350 plus a portion of this $2,000, okay? A portion of this $2,000. All right, it's going to be split equal, all right? So now it says find the total average cost per person if 40 band members attend the bowl game. So we know now that X is 40, all right, because it's 40 people, 40 band members. So all I do is take this equation right here, and I'm going to plug in the 40. All right. So when we do that, we have $350 because you got to pay $350 plus, if we take 2,000 and divide by 40, all right, that we got 200 divided by 4. That's going to be 50, right? That's 50, right? All right. So right here, 2,000 divided by 40 is 50. All right. So now 350 plus 50 is going to be $400. So each band member, all right, who's going to play in this game has to pay $400. Okay. Now there's a U try right here. All right. I'm going to with the graph portion you can do with your calculator. All right. It says what is the horizontal asymptote of the function and what does it represent? All right, so for the horizontal asymptote, if you remember how to find it, remember for the horizontal asymptote, we don't have to graph this to even find the horizontal asymptote. What we do is, remember for the horizontal asymptote, all right, we look at our rules where we look at the degree. We look at the degree of the top, and we look at the degree of the bottom. Where the degree of the top is 1, and the degree at the bottom is 1. See, r to the first, r to the first. Well, since the degrees are the same, we divide the leading coefficients. So we have 12 divided by 1. And 12 divided by 1 is 12. So we have blah, 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 blah. So the horizontal asymptote is y equals 12. But in this case, it says, what does it represent? All right, what does horizontal asymptote represent? Well, it represents the number of seconds the driver spent, all right, at the pit stop, all right? Because when you look at the graph, matter of fact, here, I'm going to let you graph it. You graph it, all right? And when you look at it, you'll see that it represents, here, I'm going to type it, actually. Let me type it. Give me a second. There we go. All right, it represents the number of seconds the driver spent at a pit stop. Because remember, with an asymptote, the function doesn't touch it. So that means that, all right, the race car driver isn't driving. Okay, he's not driving. He's at the pit stop. Okay. Now, right here, part C. Part C says the driver average speed at the pit stop is 200 miles per hour. How long does it take the driver to complete the lap, including the pit stop? All right, so all you would do is, all right, yeah, so anyway, man, the driver's average speed after the pit stop is 200 miles per hour. How long does it take, all right, the driver to complete the lap, including the pit stop? So here's our equation. All right, let me clean it up for you. I marked it up. Here's our equation. All right, there's a couple different ways to do this. You have to understand, though, that if you use your table, that's your y value, all right? But I want to show you algebraically how to do it, and then I'll show you, well, I'll point that out in class. Algebraically, we know that the average, well, hold on here, let's do this. So when you look at this, they tell us that R is the driver's average speed in miles per hour, all right? So given this equation, we know that R is the speed. So we have 12 times 200 plus 9,000 divided by 200. All right. And doing so, 12 times 200 is going to be 2,400 plus 9,000. That's going to give us 11,400. All right. Oops, 11,400. And then we divide that by 200. And we're going to get 57 seconds. All right, it takes 57 seconds for this driver to complete a stop, including the pit, to complete a lap, including the pit stop, okay? All right, now, let's look at this next problem. The Agnesi curve is a graph of a function y equals a squared divided by x squared plus x squared plus a squared. All right, so it's graph the Agnesi curve for a equals 3. All right, so what we're going to do is this. They already defined a for us. A is 3, so for part A, then change that back. Part A, we have 3 cubed, because A, this part A right here, 3 cubed, because they said A is 3. So 3 cubed over x squared plus 3 squared. So we're going to graph that, okay? So let's do that. All right, so you see I got it right here, 3 cubed divided by x squared plus 3 squared. All right, then we're going to hit graph and let it graph. All right, cool beans. So there we go. Oh, by the way, my scale is different, man. All right. Oh, no, it's not. I didn't change it. I thought I changed it. We're good. So back to the graph. All right, so when you look at this thing, okay, let's go back to the actual graph. So now looking back right here where it says find the domain and range of the function, what I'm going to do is this. I'm going to bring over the graph. All right, here we go. Let's definitely resize this thing. Make it a little smaller. All right, cool. There's the graph, okay? So now part B right here says, what's the domain and range? Well, if you look, see how this goes to the left and the right infinitely? This will never stop going left and right. So for part B, the domain, guys, it's all real numbers. All right, notice that will never stop going left or right. All right, or you could put negative infinity to less than or equal to x less than negative infinity less than x less than positive infinity. All right, so again, the double R, that double R is terrible. All right, there we go. That looks a little better. All right, so that's the domain, guys. It never ends as it goes to the left. The x values will all be used. You want -1, -2, -3. This will never stop going in the negative direction or the positive direction. Okay. Now for the range, for the range, the thing I want you to notice is when you look at the horizontal asymptote. All right, when you look at the horizontal asymptote. If you look at the horizontal asymptote and where it is, you'll see, well, we have x squared right here at the bottom, and there's no x squared at the top, so we're going to just say x is 0. Well, remember your horizontal asymptote rule: when the degree is larger at the bottom, all right, your horizontal asymptote is y equals 0. All right, y equals 0. So that's the horizontal asymptote, y equals 0. So there's a horizontal asymptote right here is 0. Actually, let me use another color so it's different. Trying to explain this out so you can have a visual. All right, that's the horizontal asymptote, meaning that blue line right there will never pass that red. It can never cross it, because remember, the function does not exist at asymptotes. All right, it doesn't cross it, it doesn't touch it, it doesn't exist there. All right, so knowing that, we know that the lowest this graph can go is 0. All right, but it has to be greater than 0. So when we talk about the range, guys, we're going to say that y is greater than 0. All right, but it is less than, what's the maximum right here? Well, 1, 2, 3. This is the maximum right here. All right, that's as high up as it will go. Remember, the range is for the y values. So the highest it would go is 3. So from 0 to 3 is where the range of this graph is, from here to here. That's as high up, or how tall the graph is. That's as tall as it would be, okay? All right, and then finally, man, part C, it says identify all the asymptotes. Well, we just did that, right? The horizontal asymptote is y equals 0. Again, you have x squared at the bottom, and there's no x at the top, so we say that you could put a placeholder there and say x is 0. All right, well, the degree is larger at the bottom than at the top, so therefore the horizontal asymptote is y 0. Okay. All right, there's a U try right here. With this U try, the chemist has 100 gallons of 12% saline solution that she wants to strengthen to 25%. The percentage P of salt in the solution by mass M can be modeled by P of X, where 100 times 12 plus X all over 100 plus X, where X is the number of grams of salt added. All right, so it says graph this function between 0 to 100. Okay, 0 to 100. So when you graph it, they simply just want you to change your window range from 0 to 100. So like this, you would go right here. Your X scale from 0 to 100 for the max. Like that. So now when I graph the equation, let me clear this out. All right, so we have at the top 100 times x, 12 plus x. All right, divided by, nope, one more parenthesis. Divided by 100 plus x. There we go. And when we graph it, oh, error. What's the error? I got an error right here. Let me figure it out. Give me a second. All right, I changed my y scale as well. I changed x from 0 to 100, and I changed y from 0 to 100. All right, so there's our graph right there. So I changed everything from 0 to 100. Y as well. 0 to 100. All right, so anyway, there's our graph. Now it says use the graph to estimate how much salt must be added to create a 25% solution. Well, I think we can go to our table. All right, I think we can actually go to our table and look for 25% solution. All right, so 25% solution would just be our y, right? So let's see, 25% solution. All right, stop. Can we just pass this right there? Okay, cool. All right, see right here, we have 20. This is over 25%. This is a little less than 25%. So I'm gonna go with that. I'm thinking right here, right there, you need about 17 grams of salt. About 17 grams of salt will get you there. So let me go back. All right, about 17 grams of salt will get you there. Okay. All right. The other way to do that is you can really just solve it. All right, so to solve this algebraically, well, we know we're looking for a 25% solution. All right, 25% solution. So we're gonna let P of X be the solution. All right, it says P is the percent of salt in the solution. So 25%. So I'm gonna go 25 equals 100 times, let me fix that, 100 times 12x, or 12 plus x, good night. 12 plus x, all over 100x. All right, or 100 plus x, man, I did it again. Plus x, okay? So now, the first thing I'm gonna do is I wanna multiply both sides by 100 plus x. And the reason I'm doing that is I want to get rid of this denominator. So I'm gonna multiply this by 100 plus x. All right, so when I distribute that, I get 2500 plus 25x equals, then I'm gonna go ahead and distribute this. So 100 times 12 is 1200 plus 100x, like that, okay? So now we just combine like terms. If I subtract 1200 over here, all right, that's going to give me 1300, right? And then 1300 equals, 1300 plus 25x, 100x. And then if I subtract 25 on both sides, I'm going to get 1300 equals 75x. And then finally divide by 75 on both sides. All right, and when I do that, I'm going to get 17.3. Repeating. So again, that's about 17 grams, which is what we got using the calculator. But man, that concludes the video, man. Like, here's the homework. Man, the homework is pretty much just like what we've done. So just give it a try. Give it a try and bring questions tomorrow, okay? Catch you later.